Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants in Oakland, California. I'm the coordinator of the webinar series on behalf of SERDP and ESTCP. Today's webinar is the first in a two-part series on managing AFFF impacts to subsurface environments and assessing PFAS-free foam. The second part of the series will take place in 2 weeks. For today, we will start with a brief overview of SERDP and ESTCP, followed by 2 technical presentations. First, Dr. Ezra Cates from Clemson University will provide details on a photocatalytic treatment system for the remediation and management of PFAS-impacted wastewaters. Ezra's presentation will be followed by a Q&A session. Then Dr. John Payne from National Foam will discuss the physical and chemical processes of PFAS-free foams that affect foam performance. John's presentation will also be followed by a Q&A session, and depending on time, we'll conclude the webinar with a longer Q&A session featuring both of today's speakers. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, you may view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you're unable to view the slides or if your screen freezes, try keying in Control and F5 to perform a hard refresh of your browser. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select the speaker and microphone, and please follow the prompts as they appear on your screen. If you continue to experience difficulties, feel free to call into the conference line shown here. You may also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for today's speakers. And in case of continued technical difficulties, you can download a PDF of the slides from the webinar webpage. The link is shown here, and then call into the conference line provided to you in your webinar registration confirmation email. Note that we will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here, and that's another way of following today's proceedings. This broadcast will be listen only. You can submit questions by using the Q&A box on your screen. Please don't use the chat function or the chat box to submit your questions. Please do not wait until the Q&A periods to submit your questions. Feel free to submit them well before we start the Q&A sessions, and we'll be going through them and posing them to our speakers. With that, I would like to introduce Dr. Robin Nisan, who is the SERDP and ESTCP Program Manager for Weapons Systems and Platforms. Before joining SERDP and ESTCP, Robin worked at the Naval Air Warfare Center's Weapons Division in China Lake, California. Robin, please proceed.
Well, thank you, Rula. I'm happy to welcome everyone today to the SERDP and ESTCP webinar. SERDP is the Strategic Environmental Research and Development Program. It was established in 1991 by Congress, and it's a partnership between the DoD, Department of Energy, and EPA. SERDP's mission is to identify and address high-priority environmental S&T opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development efforts, which will ultimately impact real-world environmental management. ESTCP, the Environmental Security Technology Certification Program, is a program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designated to transition technologies out of the laboratory and into the field. Especially important in all ESTCP demonstrations is the ultimate transition of technologies to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs, with much of SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are 4 program areas in SERDP and 5 in ESTCP. Installation energy and water program area is only in ESTCP, while the other 4, environmental restoration, munitions response, resource conservation and resiliency, and weapon systems and platforms, are SERDP and ESTCP programs managed jointly by a designated program manager. Today's webinar presents results and research and demonstration efforts that were conducted in 2 different program areas, environmental restoration and weapon systems and platforms. Environmental restoration has essentially 5 main areas of research: contaminated groundwater, contaminants on DoD testing and training ranges, contaminated sediments, wastewater treatment, and risk assessment. The weapon systems and platforms program area has 4 major focus areas: surface engineering and structural materials, energetic materials and munitions, noise and emissions, and waste reduction and treatment in DoD operations. In addition to the 2 projects that you will be hearing about on today's webinar, SERDP and ESTCP are funding a broad range of other PFAS-related projects. You can access an overview of our PFAS program as well as project descriptions using the link below on this slide. The boxes along the top of the graph illustrate workshops that have been held to develop a strategic plan for addressing PFAS issues. A summary report was prepared for each workshop to summarize the discussions and identified research, demonstration, and technology transfer needs. To view workshop reports, click the associated box. The SERDP statements of need are specific topics released as part of the annual solicitation that describe the research areas of interest for that fiscal year. Click on a statement of need to view a summary of the research need as well as a list of the projects selected under that statement of need. Within these summaries, each project title links to a full description of the project as well as to any SERDP reports that have been published as part of the project. Each ESTCP topic listed represents a single topic. Click the project title to go to that project's webpage. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. Upcoming webinars will cover a broad range of topics, including adapting to changes in the hydrologic cycle under non-stationary climate conditions, advances in stormwater monitoring and development of the best management practices for treatment, corrosion mitigation, and predictive analysis for DoD weapon systems, forensic techniques for differentiating PFAS sources, amongst others. You can find additional information about upcoming webinars at the link on this slide. So the SERDP and ESTCP Symposium will be a virtual event. It will be held the week of November 30th through December 3rd. But latest news is that we will be moving to virtual. I would like you, so you'll find out more information about that, and we would ask you to consider submitting a poster abstract and to visit the website to register. And finally, I would like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. We would appreciate it if you could take the time, a moment to complete a survey that will pop up on your screen at the end of the webcast. Hope you enjoyed today's webinar. Back to you, Rula.
Thanks, Robin. And just a reminder to everyone, the link to the PDF of the slides is in the chat box. So feel free to download them. It is now my absolute pleasure to introduce our first speaker, Dr. Ezra Cates, who is an associate professor of environmental engineering at Clemson University. Dr. Kate's research focuses on the development of advanced light and radiation-based water treatment processes for disinfection and advanced contaminant destruction. Ezra has served as a principal investigator on several research projects to develop cost-feasible destructive technologies for PFAS. He earned a bachelor's degree in environmental studies from the University of North Carolina in Asheville and a doctoral degree in environmental engineering from the Georgia Institute of Technology. Ezra, please get us started.
Thank you very much for the introduction, Brula. It's a pleasure to be here. As she mentioned, I'll be presenting on photocatalytic destruction of PFAS. And with relation to groundwater, this is an ex situ treatment method with applicability toward treatment of purge waters from monitoring operations for disposal or for ex situ remediation of groundwater. I'll go over the objectives of the project and some background on photocatalysis in general. And then I'll present results, including phase 1 of the project, which has been completed, and then some of our work from phase 2, which has been going on only since late April, but we're already getting some results there. And then the next steps of where we're headed after that. Our objectives are to optimize PFAS destruction using bismuth oxyhydroxyphosphate, which is a novel semiconductor photocatalyst that we have developed. We're also focusing on innovation in reactor design for the photoreactors, which use ultraviolet lamps, with the objective of increasing efficiency of photocatalytic treatment overall. Ultimately, we want to develop a robust and deployable treatment system that can be used on-site for smaller scale wastewater and IDW applications. We're using a three-pronged approach that really covers sort of all levels of photocatalysis, including fundamental study of PFAS photocatalytic mechanisms and innovation of the catalyst materials themselves. So there's a material science aspect here, but at the same time, we're looking at, again, the reactor design and improving efficiency of the overall process, including some process engineering considerations, such as the water matrix and any water preconditioning that might benefit this process. This diagram here is actually applicable to the next slide, so I might be coming back to it. Just some background on photocatalysis and photocatalytic water treatment. I usually like to preface these talks by mentioning that, at least in academic circles, these days, photocatalytic water treatment is sometimes greeted with sort of a collective eye roll, in the sense that people are kind of have the mentality of, oh, you're still trying to make this work, huh? And I actually share in that mentality to a great extent, but I started to sort of compare this field to the field of chiropractics, in that there are many chiropractors who give practical, effective treatment to lots of people and improve their lives. But at the same time, you encounter chiropractors who claim they can, I don't know, cure your allergies with a spinal adjustment and then bill your insurance company for $800. Photocatalysis is similar in that respect. There are some of us who try to maintain a practical outlook, but there are also many, many publications in the literature that are much less practical or much less transparent and lacking in context. So I try to urge people not to let the prevalence of the latter sort of affect the validity or the credibility of the former. So we're looking actually at, well, first of all, you may be familiar with ultraviolet TiO2 process. Titanium dioxide is the most commonly mentioned semiconductor photocatalyst. However, it doesn't work for PFAS destruction because it mainly generates hydroxyl radicals, which are not effective for reacting with PFAS. There are alternative semiconductors that have been used to degrade PFAS. And I've listed some here. We're mainly focusing on this one, the bismuth oxyhydroxyphosphate, or BOHP. All of these utilize what I call a direct heterogeneous reaction or direct photocatalysis. So they do not rely on generating radicals, But instead, as shown here, we have more direct interaction with the target contaminant. So this typically takes the form of particulate semiconductors suspended in water, which are flowed through a UV photoreactor. Excitation with UV photons excites electrons from the conduction valence band of the semiconductor into the conduction band across the band gap. And I'll be referring to that as charge separation, which generates two types of charge carriers, conduction band electrons and valence band holes. We then want these charge carriers to migrate to the surface of the particle, where they can then participate in redox reactions. So ideally, the target contaminant adsorbs to the particle surface and becomes oxidized by the valence band hole, initiating degradation. We also want the conduction band electron to be scavenged, usually by dissolved oxygen. So for those of you in the more microbial remediation fields, this is somewhat similar to microbial processes. We need an electron donor, an electron acceptor, but instead of using enzymes, we are using UV photon energy. Because it's a direct mechanism, adsorption of the target contaminant must be favored. So the surface properties of the semiconductors become fairly important. Research on larger scale photocatalytic reactors and their performance is very much lacking in the literature. Most of the studies that have been done use bench scale systems such as this one shown here. So we've found that when we started to scale things up, we actually quickly started learning a lot of things that weren't yet in the literature. And then I want to reiterate that generally, in my opinion, photocatalysis is only suitable for smaller scale applications rather than sort of municipal scale water treatment. Also, makes much more sense for things like PFAS, where conventional methods don't really apply. So here's some background on the specific catalyst we're using. We discovered this material and found that it was more effective than any of the other materials in the literature. We haven't compared it to every other one directly, but it seems to certainly rank among the most effective semiconductor photocatalysts for PFCA degradation. They're in the form of microparticles that we prepare through a hydrothermal synthesis reaction. And we've done extensive testing in bench scale experiments as well as larger scale experiments, and I'll be explaining both results. Our studies have found that BOHP can rapidly degrade long-chain PFCAs, as shown here with the perfluorodecanoic acid, nanoic acid, and PFOA. But when we test shorter chain PFCAs, we see much slower degradation or no degradation at all by the catalyst. And that is a function of their adsorption properties. So we don't get good adsorption of the short chain PFCAs, so the photocatalysis is less effective. The same goes for Gen X. It doesn't adsorb well, and we don't see effective photocatalytic degradation. And the perfluorosulfonates are too hard to oxidize in this case, so we don't degrade those with this catalyst either. With PFOA, we see 65% recovery of fluoride after 120 minutes. So we are getting a good degree of, or sort of a typical degree of mineralization. And based on the intermediates that show up during PFOA degradation, it appears to be a pretty standard stepwise chain shortening. So those results are in the bench immersion reactor shown here, which is simply a UV lamp put down in a suspension that's magnetically stirred with a water bath to keep it cool. Of course, we want to look at larger scale systems. So we've tested a commercial photocatalytic reactor made by Purifics, and this system normally uses TiO2, but we replaced that with our BOHP catalyst. And it's important to note that the actual photoreactors are quite different here. These are very long annular reactors with a narrow annulus width, and water flows through here at a high turbulent velocity. And it's overall a lot of UV lamp power relative to the volume of the reactors. So because of these, the difference in the configuration of those photoreactors, we observed different results in PFCA degradation. I also want to mention that If you're not familiar with UV lamps and mercury lamps, there are really two sort of flavors of these. First is the ozone generating lamps, which have emission at 254 nanometers primarily, shown here. But there is also a secondary emission peak at 185 nanometers, which is in the vacuum UV range. And this turns out to be quite important because these photons can directly photolyze most organic contaminants, including most PFAS. So that then opens up the opportunity for not only photocatalytic degradation with the semiconductor, but also direct photolysis from vacuum UV. The other type of lamp is a ozone-free lamp, which only includes this emission peak here. And it turns out that most academic studies use these ozone-free lamps. So one of the things that we've been sort of advertising is that it makes sense to go ahead and use the ozone-generating lamps because they have the same energy efficiency, but this emission peak at 185 turns out to be quite useful. And that shows up in the results of the commercial photoreactor. We observe not only degradation of the long-chain PSCAs, but actually all PSCAs, as well as Gen X, were degraded at essentially the same rate. And interestingly, that occurred whether or not we included the catalyst. So it was kind of indifferent to the presence of the BOHB, indicating that this is really entirely photolysis driven due to that 185 nanometer vacuum UV emission component of the lamps. So on the one hand, you might be thinking, great, we can degrade a wider range of PFAS and we don't even need the catalyst, so why not just go all in on this vacuum UV photolysis? Well, the reason we're still pursuing photocatalytic degradation is that our PFOA degradation specs, our energy efficiency per order that we observed in the bench reactor was 25 kilowatt hours per cubic meter. Whereas PFOA degradation in the commercial reactor, which was mostly photolysis, took about twice as much energy to achieve the same amount of degradation. So this tells us that we shouldn't discount photocatalysis completely because there's an opportunity for greater efficiency. What we need to do is figure out how to take advantage of photocatalysis using the reactor design, which apparently was not achieved in the commercial reactor. So at this point, we started to move toward the concept of hybrid photolytic photocatalytic reactors, where we want to be aware of both of those processes and potentially optimize them both for better overall efficiency. So we started to do some comparisons between our immersion reactor, and then we constructed a scaled down version of the commercial reactor. So we have these smaller annular reactors that emulate all the conditions of the commercial reactor, but they were much easier to control experimentally. And in both cases, we had the option of equipping them with either a ozone generating lamp or an ozone free lamp to do those comparisons between the presence or absence of the vacuum UV. What we found was in the immersion reactor, which is sort of milder mixing conditions and less UV input relative to the reactor volume. For 254 nanometer only, we don't observe any PFOA degradation without the catalyst, and then when the catalyst is added, we have clear degradation. When we switch to the combined 185, 254 nanometer, the ozone generating lamps, we see a greater degree of photolysis in the absence of the catalyst, but also the presence of the catalyst still has a very obvious effect. So we're seeing this additive effect of photolysis and photocatalysis. In the annular reactors, on the other hand, with 254 nanometers, we see an effect of the catalyst being present, but with the ozone generating lamps, again, it's relatively indifferent to whether the catalyst is there or not. So to figure out why that was the case in the annular reactors, we looked at all the sources of efficiency losses in photocatalytic systems, and I've listed them all here. These first three are not really affected by reactor design, so I'll skip to the last two, which are. And that includes wall losses, where you have excess UV is absorbed by the photoreactor wall and thereby not utilized. And you can also have saturation losses, where again, you have high intensity UV exciting these semiconductor particles, but you're generating those charge carriers faster than they can actually react with the contaminants. So this is also sort of a mass transfer limitation. And this concept is portrayed here in a photocatalytic system. As you add more and more light intensity, but keep the volume fixed, you'll start to see diminishing return on investment in terms of the photocatalysis rate, and that would be indicative of poorer efficiency. So we think with the annular reactors, we're operating somewhere in this regime, and then with the immersion reactors, we're operating more over here, where more of the UV is being effectively used. And this sort of implies that the less the UV intensity is, or the lower the UV intensity, the more efficient it will be, because you're more likely to be able to use all the photons put into the system. But there is a trade-off between efficiency and kinetics. If you go to higher intensity, you can increase the kinetics, but potentially lose efficiency. So it seems clear to us at this point that the best option is to scale back the intensity a bit for the benefit of that efficiency and do a sort of slower type photocatalytic treatment system that might have a little bit larger residence time and a larger footprint, but more effectively utilize the energy that's put in. And we showed this once and for all by constructing annular reactors with progressively larger annulus widths. And what we found is, as we made the reactor volume larger but kept the lamp power fixed, we got greater and greater efficiency, definitely with photocatalysis and to some extent with photolysis as well. And we also saw more and more difference when the catalyst was there versus just relying on the photolysis. So it seems if we want to take advantage of photocatalysis, we have to use less power relative to volume. And that's sort of illustrated here. Anytime you have a UV lamp submerged in a suspension, the vacuum UV can only penetrate about a millimeter or two into the solution. So all of the photolysis will occur very close to the lamp. So I've labeled this the photolysis zone. But the UVC can penetrate much further away from the lamp and is actually much more intense. And so we may as well utilize this UVC emission by having the photocatalyst present and keeping the reactor wall spaced somewhat from the lamp. So we decided that the annular reactor configuration isn't really the way to go. Instead, we started pursuing these stirred tank batch reactors in series, and this is ongoing work. But the idea here is that we use an impeller for mixing, which allows us to control the mixing rate or the turbulence independently of the flow rate through the reactors, which is important. And what we're working on now is optimizing the spacing of the lamps within the reactors, the volume of the reactors, as well as the catalyst concentration and the mixing power in order to see how much additional efficiency enhancement we can get just by playing around with these sort of geometry issues. I've also come up with an entirely new hybrid photocatalytic photolytic reactor design that I think could potentially fix a lot of the issues that we've had as far as the competition between photolytic and photocatalytic mechanisms. But we're working on the proof of concept for that. If it's successful, we may abandon this configuration shown here. I'm not really sure yet. We've also looked at the effects of water matrices, which is very important because with photocatalysis, there is potential for substances in the water to quench photocatalytic reactions and detract from the treatment efficacy. So I've listed some of the potential culprits here. I don't have time to go through this data in detail, but I'll say that we've found the presence of few mixed substances and short chain organic acids really isn't a big deal. We can handle that by adjusting pH down to either 4 or 3 in order to protonate those acids, in which case they will not strongly adsorb to the catalyst, whereas the PFAS will still be negatively charged, so we can basically make the system more selective toward just the PFAS. The most problematic water constituent we found is chloride and also sulfate. Both of these, when present in high concentrations, result in slower and slower PFOA degradation kinetics. So if you're dealing with waters that have elevated chloride or sulfate, we should really consider whether photocatalysis is the best option for that. The chloride acts as a whole scavenger, whereas the sulfate acts to neutralize the positive surface charge of the catalyst. So we see actually a plateauing effect with sulfate addition. Our next steps, we are, first of all, as I mentioned, optimizing these stirred tank photoreactors to improve efficiency. But really what we're focusing on now is development of next generation catalyst material, which is something we haven't really allowed ourselves the time to do yet. But from a materials science perspective, I believe there are many opportunities to improve the catalyst itself, and then those improvements will then translate into efficiency improvements of the overall process. Ultimately, we want to do a batch pilot study using real investigation-derived wastewaters, and of course do scale up and cost analysis so people like yourselves can properly compare this technology to other technologies that are available. Just a few final words on the next generation catalyst development. Our goals here, as far as optimizing the particles and the composition of the semiconductor, we want to achieve higher surface area, more positive surface charge so we can better attract PFCAs, and that can be done via doping strategies. We want to reduce the presence of bulk phase oxygen vacancies, which are a source of electron hole recombination, as well as a source of instability in the catalytic activity. And we also want to explore looking at heterojunction materials wherein two semiconductors are used, which is another strategy for improving charge separation. Overall, this BOHP material that we've been using seems to be really picky. Every time we try to change the synthesis conditions in order to slightly alter the material, the material does not respond favorably. So we want to look at compositional variations that are a little more stable so that we can perhaps manipulate them more and have greater freedom in synthesis conditions. We've actually recently discovered that BOHP really belongs to a wider family of bismuth oxyphosphate materials, which is shown here. This is what I consider the parent structure, which has this additional bismuth site with partial occupancy. And in BOHP, we've replaced this with hydrogen actually, but we can also replace this site by doping with any number of monovalent, divalent, or trivalent ions. And what that will do is allow us sort of a means of tuning this material to our liking as far as improving the stability and also the presence of bulk oxygen vacancies. So we've hypothesized that going to larger ionic radius dopants will give us more favorable properties, and we're in the process of testing that hypothesis now. All right, and these are the final required slides. So just to reiterate, we are developing a novel photocatalytic treatment process, ultimately for a deployable system that can be used to treat PFAS in investigation-derived wastewaters. We're also pursuing application toward landfill leachate treatment as part of a EPA-funded grant. And that is all I have for today, and I'll be happy to take any questions.
Great, thank you so much for a fascinating presentation. Just a reminder to everyone, please submit your questions using the Q&A box on your screen, not the chat box. We've received lots of questions on this first presentation that we're gonna relay to Ezra for the next 10 minutes, and then we'll try to get to any outstanding questions depending on time towards the end of the presentation. So I'll start with this question from the City of Phoenix Aviation Department. What is the upper limit concentration in the influent that can be treated using the system you described?
Yeah, that's an interesting question. So really what we've observed is the higher the concentration is, the greater the efficiency, because this is sort of an adsorption limited process. So higher concentration will then drive more of the target contaminant onto the catalyst surface, which will then improve the degradation kinetics, or at least the mass rate degradation. I can see perhaps there might be a problem if you go above the critical micelle concentration. I'm not really sure what would happen if you're operating in the presence of micelles, but overall, high concentration is a good thing.
Great, thank you. This next question is a really interesting one from the DEFCON Army Research Lab, and it relates to the byproducts that you may be producing through this process. This gentleman indicates that the reaction mechanism slide shows that a perfluorinated carbon chain is formed, perhaps without the hydrophilic components. If that's the case, is the idea that the perfluorinated carbon chain would then be easily separated from water, and that makes it easier to dispose of or more safer to dispose of? Ezra?
So if I'm understanding the question correctly, it's maybe a bit inaccurate to say that it results in a perfluorinated carbon chain only. What happens is it results in progressively smaller chain carboxylic acids. So once the carboxylate group is cleaved off of PFOA, for example, then there are a series of reactions resulting from the instability of those products that results in basically a 7-chain carboxylic acid. So it sort of gets reoxidized. So the main intermediates of PFOA degradation would be the 7-carbon, 6-carbon, 5-carbon perfluorocarboxylic acids. And so as we get to the shorter PFCAs, the photocatalytic degradation would be less and less efficient. So that's when we would be relying more on the vacuum UV degradation to get full mineralization. Though we have observed, interestingly, we get greater mineralization than you'd expect, given that if we spike some of these short chain PFCAs in individually, they don't get degraded. But when they are formed as a result of longer chain PFCAs being degraded, then they seem to be degraded more effectively. So it's almost like the longer chain PFCAs have irreversible adsorption to some extent to the catalyst, which helps them get chewed away more completely and mineralized than if they were just initially spiked as short chain PFCAs, if that makes sense.
Yes, thank you so much, Ezra. This next question is from Shell. And I know you talked about matrix effects, and you suggested that a potential use is with landfill leachates. Are there any plans for you to potentially use this product or your process on AFFF concentrates, or do you anticipate the matrix effects to be overwhelm the system?
Yes, to be honest, I'm not very familiar with the properties of raw AFFF. As I mentioned, higher concentration is probably favorable for photocatalysis. The one problem I can see there is that I believe AFFF can contain more zwitterionic and cationic PFAS, which I don't think we could effectively degrade through photocatalysis, though I believe photolysis would take care of those pretty readily. So with the contaminated groundwater, at that point, most of the cationic and zwitterionic PFAS have been sort of filtered out by the soil, from what I understand, and strongly associated with the soil. So then we've been designing our technology to handle mostly the anionic PFAS. So that's the main difference I can see if we were to switch over to AFFF. But unfortunately, I can't answer that question more thoroughly, as that really hasn't been our focus thus far.
Well, thank you for taking a crack at it. The next question is an important one. I want to make sure that you point attention to it. It's from the Air Force Civil Engineering Center. You showed a lot of data on the carboxylic acid and GenX. So the question from AFFF is, does this technology work on PFOS and some of the sulfonic acid?
And the answer is no, it does not. There have been a few reports in the literature of photocatalytic degradation of PFOS. I personally am very skeptical of them. I think it is possible to do it. It has to be through a reductive photocatalytic mechanism. And we've actually achieved that using not BOHP, but another bismuth phosphate catalyst. It was not efficient enough for us to want to publish it. It was a very minor amount of PFOS degradation, but we did do that reductively. I mentioned a alternative photoreactor design that we're testing. One of the benefits of that design is you can do multiple photochemical processes kind of within the same reactor without affecting the photocatalytic efficiency. So that would then allow us to spike in at certain points within the treatment train, things like sulfite, for example. So if you really wanted to target PFOS, you could use the photocatalysis as sort of a pre-treatment and then take care of the sulfonates with sort of a final flow through past the UV lamps in the presence of sulfite, which is known to degrade those sulfonates.
Great, thanks for elaborating on the treatment train approach. It's an important consideration. You didn't talk a lot about cost. Are you at a stage yet where you can discuss cost and performance information, or is that something you're working on next, Ezra?
Yeah, I think most of us in the destructive treatment area of the PFAS realm, we're at the stage where we're mainly just looking at the EEO, the electrical energy per order of destruction, as kind of a raw or basic indicator of cost. So right now, our best EEO is about 25 kilowatt hours per cubic meter. Other technologies, that ranges from, I think, around 5 and then all the way up to the thousands. So I would say our EEO value is promising. And it all kind of depends on how successfully things can get scaled up, I guess. I'm not sure these other technologies like plasma treatment, which have lower EEOs at this point, if they can be scaled up or if they have water matrix issues as well. But given the EEO we've achieved thus far, we think we have a lot more opportunity for efficiency enhancement. So I think photocatalysis should still be investigated and could definitely be promising. Other sources of cost would be water conditioning. We do need to acidify these waters down to pH 4 in order for it to be effective. But the EEO value I mentioned, that's mostly the electricity used for the UV lamps. And on top of that, you'd want to add electricity use for any mixing and also catalyst recovery. But based on our experience with that commercial system, the UV lamps are really the vast majority of the energy costs. So separating the catalyst with a membrane ultrafiltration process does add sort of a marginal amount of energy use.
Great. And a question related to the EEO values issue from the University of Cincinnati. Can you elaborate on the matrix of the water you use? What kind of water is treated for the determination of the EEO values you reported? And what are the EEO values in real water matrices or in environmental matrices?
Yeah, great question. So EEO is usually reported either using relatively pure water or in a full real water matrix. So the values that I listed, that was pure water, so it's essentially acidified DI water with the contaminants added. But from our quenching analyses, like for example with the chloride, We see slightly elevated chloride levels would result in kinetics about twice as slow. So our EEO value would be about twice as much in a water matrix affected by chloride. And as far as adding everything together, I'm not really sure. We have done some tests with actual IDW, and it was about twice as slow the degradation. So I would say that the values I listed, if you want a more accurate real water matrix number, to double them at this point.
Great, thank you so much, Ezra. Please stay on the line. We'll try to get to unanswered questions towards the end. But at this point, I would like to go ahead and transition to our next presentation, which will be given by Dr. John Payne. John is the Foam Research and Development Manager at Angus International Safety Group, the parent company of National Foam. In his role, John develops PFAS-free firefighting foams and brings them to global markets for civil and military aviation, marine, fire and rescue, and petrochemical end users. John's work focuses on understanding how the bulk phase and interfacial chemistry of foam formulation components affect foam properties and fire performance. He leads a team of scientists who have developed several PFAS-free foams, and he earned a bachelor's degree in chemistry and a doctoral degree in physical chemistry from the University of Bristol. Thank you for agreeing to give this presentation, John. Please proceed.
Thanks, Rula. And I'd like to talk about the physical chemistry processes that are involved in firefighting foams. A brief background, then the technical objectives of the project, particularly focusing on the physical chemistry measurements and processes that we've looked at, some fire testing of candidate formulations, and then conclusions and benefits to the DoD. I think everybody knows the background to AFFF. Fluorosurfactants, such as the one shown, which is a zwitterionic fluorosurfactant, give aqueous film-forming foams some really important properties. They help with spreading the foam over the fuel, they help with foam stability to destruction, and they help with vapor suppression. So they give critical properties to foams. And the challenge that we have is to try and match that fire performance with new foams that don't contain fluorine or PFAS. An even greater challenge is to do that with foam concentrates that have acceptable physical properties, because the aim is to have foam concentrates with the same properties, so we can just change the foam. We don't have to change all the hardware as well. The technical objectives were to increase our understanding of the physical chemistry processes that underpin foam. So what's happening when we generate foam and when we deploy onto a fire. Then to use that knowledge to develop some model PFAS-free formulations and test them in the 28 square foot fire test. A big part of the project was a life cycle analysis to compare C6 fluorocarbon and PFAS-free foams. And unfortunately, I won't be talking about that today. I just haven't got the time on the slides, but that will appear in the final report, some detailed summary of that work. So that should be coming out fairly soon. Our technical approach was to say, we start with a foam formulation, and that contains water, surfactants, and other components that give it a certain surface chemistry. That could be surface tension or viscosity. And those properties mean that when you put that solution through some sort of a device, which could be a nozzle, it will generate foam. And that foam will also have properties such as bubble size, rheology, vapor resistance, and those properties determine how good it is at controlling fires, how long it takes to extinguish, what fuel types it works on, what water type it's compatible with. And that was the aim, was to try and understand as much as possible of this process, accepting that it's very complicated. We're not going to understand all of it, but the more we can understand, the better. Alongside that, we want to look at, when we're choosing components, what's the sustainability of those materials? When the foam is used, what's the fate of those materials, and what sort of exposure will there be? And finally, can we reduce the environmental impact of the foam manufacture, and use. We don't want to replace PFAS with something else that will give us regrets at some point in the future. So the whole project is about understanding the chemistry and environmental impact of what's going into our foam. In a typical foam, we'll start with water. Water is very important. There's some very good things. But we also have hydrocarbon surfactants. These are surfactants where the hydrophobic group, the water hating part, is a hydrocarbon. These can be made from oil, synthetic surfactants such as anionics and non-ionics, or they can come from natural sources. Typically, these would be protein or polypeptide surfactants. And we decided from the beginning that we would not consider siloxane surfactants as part of this project. Because of the concern about biodegradability, we didn't want to replace PFAS with something else that might create a problem further down the line. They may or may not contain solvents and water-soluble polymers. Those are the key components that affect foam properties, but we also have other components such as corrosion inhibitors and pH buffers, which again, I'm not going to talk about those because they're not involved in the physical chemistry and the surface chemistry. So our first component to consider is the primary surfactant. And what this does is, its job is to generate the foam by rapidly lowering the air-water surface tension. So when our foam solution goes through that nozzle and air bubbles are dragged into it, the primary surfactant gets to that surface quickly to stabilize the surface. We can do some really basic surface chemistry on this, which gives us some really good information. So the graph on the right shows the equilibrium surface tension plotted against the log of the surfactant concentration. And you can see that on the left-hand side, it comes down in a fairly linear fashion, reaches a certain point, and then plateaus. And that point, when it changes direction, is what we call the critical micelle concentration. So to the left of that line, all the surfactants in solution are available as monomers. And they're in solution and they can do things, they can react. When we go to the right-hand side, the surfactants start to aggregate in solution and form micelles or some other aggregate. This is a very important thing to know, the critical micelle concentration, because in effect, surfactants that are in micelles aren't doing very much. They're not available enough to get to that surface and absorb. So we want the CMC to be as high as possible. Something else we can tell from this graph is the gradient of the left-hand side is obviously d gamma by d log C. And if you look at the Gibbs equation, which is in the graph, the surface excess, lambda, can be calculated from the gradient of that line. The surface excess is the excess concentration of surfactants at the interface compared to the bulk phase. And from that, we can calculate the area that each surfactant molecule occupies in the surface. And again, that's a really important piece of information. Intuitively, you would think that the closer packed those surfactant molecules, the better that foam is going to be, the more stable the surface. And we find that that is in fact the case. So by doing this measurement, we can understand how much area each surfactant occupies, and that tells us a lot about the foam properties. But it's not just how low can you go with surface tension, but how quickly can you get there. So we use a bubble tensiometer to measure the rate of surface tension reduction, or the dynamic surface tension. Again, you can see on the left-hand side, we've got a graph of surface tension against time in milliseconds, sorry, log time. And again, by taking the gradient of that line, which is almost linear, we get E gamma d log T, and that can give us some information about the absorption rate and the diffusion constant and how quickly the surfactants are getting there. So with some quite simple techniques, we're learning how fast the surfactants are getting to the surface and then how much space they're taking up when they get there. And these are all very important things to know. Why do we need to stabilize that interface? On the left-hand side, you can see a graph of surface tension against concentration or a surfactant package. The black line is in seawater, the red line is in freshwater, and you can see that the equilibrium surface tension is about the same. The gradient of the line on the left is about the same, but the CMC is very different. There's probably about an order of magnitude difference. And when we make foam using those solutions, you can see on the left-hand side in freshwater, we've got a nice bubble distribution. We've got lots of small bubbles and some medium-sized ones. But when we do that in seawater, we've got very, very large bubbles. And as a general principle, big bubbles are bad and small bubbles are good. So as I said before, the higher CMC means you have more monomers in solution that can get to that surface and adsorb. So instead of those bubbles coalescing to form big bubbles, we can stabilize them and give a small bubble size. What's happening? Well, if we have a charged surfactant, say it's got a negative charge on the head group, then when those surfactants pack together in a micelle, let's say a spherical micelle, then we have an electrostatic repulsion of all those head groups. And in freshwater, that strong repulsion disfavors micelle formation, so the CMC is high. But when we do the same thing in seawater, we've now got all these salt ions, we've got sodium ion and chloride ions, and they shield the charges and allow them to pack better and a lower concentration. So when we try and make foam with a charged surfactant in freshwater, we get a nice foam, but in seawater, because the salt shields the monomers in the aggregate, we don't get a good foam quality. Now the mil spec that we're trying to pass is a fresh and seawater spec, so we need to find a way to get good foam in seawater. And the way to do that is to increase the CMC. The graph on the right shows another surface tension against concentration graph, but this time it's an amphoteric surfactant, so it has no net charge. And now you can see the two graphs are almost exactly the same. So by switching the type of surfactant from a charged to either a non-ionic or a zwitterionic amphoteric type, we can get better foam qualities in seawater. The other thing we can do is use a solvent. We can put a solvent into the formulation that will help solubilize surfactants to increase the CMC, but as we'll see in a moment, this can have a negative influence as well. Bubble size distribution is important, and this is one of those areas in foam, and there are lots of these, where it's not always obvious what you want. Small bubbles are more stable because the excess pressure inside the bubble is proportional to 1 over the radius of the bubble. So smaller bubbles have a higher pressure inside, which means they have a stronger film to stabilize and resist that pressure. When vapor diffuses through a foam blanket, it goes through the bubbles. So it jumps from one bubble to the next. And clearly, the smaller bubbles we have, the more bubbles it has to jump through. So that gives us a higher vapor resistance. And finally, if we have a wider size distribution, we get better flow. The foam on the left is quite structured, and that will be quite a stiff foam and will not flow very well. Whereas the foam on the right, with a much wider bubble size distribution, will flow because the bubbles can tumble over each other. Now, the one on the right's got bigger bubbles, so that will be maybe less stable, and so it's not obvious which of these is the best one for fire performance. Now, as well as foam generation, creating a new surface, so does foam spreading. As the foam blanket spreads across the fuel, it generates new surfaces, and at time 0, those surfaces have a high surface energy. And so that energy will oppose the spreading of the foam. And that surface tension will give the foam an elastic character. Foam can behave like a solid, but it can also behave like a liquid. And what we want for spreading is a liquid foam that will flow over the fuel. So the rapid surface tension reduction that we get from our primary surfactants makes the foam more viscous and less of an elastic property. So again, the primary surfactants, because of their behavior, are helping the foam to spread. And primary surfactant is really all about, in our fire test, is about controlling fire, getting that foam to spread quickly and getting the fire under control. The problem with primary surfactants is they adsorb very quickly, but this is a dynamic system. So they also desorb out the surface very quickly as well. So they're going in and out very fast, and their residence time at the interface is quite short. And what that does is it makes holes in the interface and introduces a weakness. So we can add a secondary surfactant, and this is quite slow. It adsorbs more slowly than the primary surfactant, maybe because it's less soluble and doesn't diffuse as quickly. Maybe it's got a larger size, but it's just a bigger molecule. And the primary surfactant still probably dominates the surface, but now we're introducing this secondary surfactant. It makes the interface more elastic and gives us a more stable foam. But it's really important to get the right combination and the right ratio of these two surfactants. Otherwise, you can get foam properties that aren't helpful. I mentioned solvents. Glycol solvents are quite widely used in foams to increase the solubility of surfactants and to raise the CMC. And these glycols or glycol ethers are typically used, and they're known as foam boosters because they increase foam properties. But again, they're doing something good in helping the surfactants, but they also have a downside because the use of solvents in foam means that when the foam is applied forcefully to a hydrocarbon fuel, we get emulsification of fuel droplets in the foam, and they can ignite. Particularly when you start doing the burn back phase, you can get flaring of those fuel droplets and the foam can be destroyed. So fuel emulsification is a bad thing. The other problem with solvents is they increase the biological oxygen demand of the foam concentrate. And quite often, if you have a spillage of foam, for example, into a watercourse such as a lake or a pond, which is not moving water, then degradation of the surfactants can give rise to oxygen depletion, which can be quite detrimental to the aquatic life. So we really want to try and minimize the biological oxygen demand. And again, that's an area where solvents are giving us some good properties, but they also have a downside. This is probably the most important part of the formulation because surfactants by themselves don't give us a stable enough foam. We need to add something else that will give the foam more structure. And what we use are water-soluble polymers. Polymers can have three distinct behaviors in foam. If you look at the blue polymer, it's not surface active. It's solution, it's in the bulk phase, so it's affecting the viscosity, but it's not interacting with the surface. And that's one behavior that we can see from a polymer. The yellow polymer is actually surface active. It has hydrophilic and hydrophobic segments, and it will adsorb at the surface. And finally, the red one isn't surface active in its own right, but it will interact with a surfactant monolayer at the interface. And what these polymers are doing is we're starting to build structure into our foam. And this is really important for vapor suppression, because the more structure we can build in, the harder it is for those fuel molecules to force their way through the foam and to ignite when they reach the air. Non-absorbing polymers. These have been used for a long time in foams, and they're generally very large polysaccharides. Molecular weight, typically 10 to the 7, so very, very big polymers. And they're not surface active, they don't go to the interface, but they do increase the bulk viscosity significantly, and they slow down drainage. So our foam drains much more slowly. Typical AFFF drainage time might be 2 to 3 minutes, but by putting in these large polymers, we can slow drainage times down to several hours. So they make the foam more stable to drainage. But they also, because they occupy so much space and because they're so big, as the foam tries to drain out of those lamellae, it drags the polymer with it, and that creates an osmotic pressure to try and force the polymer back. So again, it's almost like an elastic effect that inhibits the lamellae from thinning and increases the foam stability that way. So these are widely used in foams. The downside, of course, is that they make the foam concentrate very viscous, and we have non-Newtonian pseudoplastic concentrates that are certainly not drop-in replacements for current AFFFs. As I said earlier, foam can behave like a liquid or a solid, and we use rheology to measure the transition point where the foam structure breaks down and instead of being a solid, it starts to flow. And we know from our experience that as you increase the structure, then you increase the yield stress, which is the point where the structure breaks down. If you look at our primary surfactant alone, it's quite a runny, quite a liquid foam. Yield stress is quite low, maybe 3 or 4 pascals. The secondary surfactant makes it more elastic, so now we're up to maybe 6, but then putting in a polymer introduces the yield stress even more. So it makes our foam more solid. And we know from experience that if the foam is too thick and too solid, then it doesn't flow. It doesn't extinguish because it sits in the middle of the pan and doesn't spread to the outside. But you can also have a foam that's too thin. If it's not thick enough, if it's not robust enough, where you apply fresh foam to the foam blanket, it opens the blanket up and exposes fuel, and that fuel will burn because it's hot. And we've seen many times foams where you get continued burning at the point of impact until you stop foam application, and then the foam blanket will close up and seal. But that's not, you don't want that to happen. You don't want continued burning. A type of surfactant that's also used, which is surface active, is a polypeptide, also commonly known as a protein type foam. And polypeptides in solution, again, they have hydrophobic and hydrophilic portions, and it arranges itself in a structure so that all the hydrophobic bits are inside, away from the water. When it reaches the interface, it rearranges its structure, which is called denaturing. And so all the hydrophobic parts are now in the air, hydrophilic parts are in the water, and this is almost irreversible. This adsorption is so strong that once the protein is there, it really doesn't want to come off. So this gives us a very, very stable interface, which is very good for vapor suppression. The problem is that we have a very stiff foam, and it's very slow spreading. And for aviation purposes, which is what we're looking for, it's too slow. It would not get anywhere close to passing a mil-spec type test. These foams are widely used for tank fire protection, where the burn back time and reignition is far more important than a rapid extinguishment. But for aviation, by themselves, they're not really suitable. So using the techniques that I described, we developed a series of foam concentrates and developed a candidate for optimization that contained 3 components: the primary surfactant package, our secondary surfactant, and a non-absorbing polymer. And we ran these through a software package with a number of fire tests to statistically optimize the performance in the 28 square foot pan with freshwater and heptane. Now, I have to say, at this point in the project, we thought the Miller test might be moving to heptane. Maybe it's going to stay with gasoline, we're not sure. But the diagrams, the top one is the extinguishment time, and the bottom one is burn back. And you can see that extinguishment time is really dominated by the primary surfactant because it gives us that foam properties and it gives us the spreading. The secondary surfactant has not much effect, and the polymer really not much effect at all on extinguishment. Where the polymer is important is in burn back time. Adding more polymer gives us a more stable foam, slower draining. And using this software, we were able to optimize and develop a formulation. These are the test results in the standard Miller test, 28 square foot pan with the normal 2 gallon per minute nozzle with the spreader tip. And we have a range of test results. These are some of the typical ones. You can see in the drawing, in the pictures below, 90% control is when we have basically got the fire under control. 99% is when we have a few edge flickers, and then we have extinguishment and the burn back. The target for the test is extinguishment in 30 seconds and then a 6-minute burn back time. That's the current standard on gasoline. On heptane in freshwater, we controlled very quickly, 90% control within 18 seconds. But you can see there's quite a long time between control and extinguishment. And that's because we probably don't have a good enough vapor suppression to get those edge flickers sealed. But the burn back time is good. And generally speaking, PFAS-free foams can give good burn back times, normally longer than AFFFs. And then the other extreme, gasoline fuel, which is a much more difficult fuel to control because it's more volatile. The surface properties are similar to heptane, but it has more volatile components. And in salt water, again, we've got a pretty good control time. Within certainly below 30 seconds, we've got the fire pretty much under control. But now we have a very long time between control and extinguishment. And again, what that's telling us is that we need to improve our vapor suppression of that foam to get that time down. Again, the burn back time, a little bit short. We probably need to improve that a bit as well. I mentioned a while ago that the foam properties are a function of two things. One is the foam solution, and the other one is the hardware or the device that you use to generate the foam. And the current MILF nozzle is shown at the top in the picture. It's got large aspirating holes, so we get a lot of air dragged into the foam stream, which gives us high expansion ratio. But it has a very short barrel, which means the foam doesn't spend much time in there. So we're not able to put much work into the foam to develop structure. So for AFFFs, which don't work by structure, they work by film formation, this is a good nozzle. And you can see that in one of our formulations, we get an expansion ratio of almost 10. Drainage time is around about 5 minutes. Just as a comparison, the ICAO test, which is used in most of the world for civil aviation, uses a different nozzle, which has a much longer barrel. It has smaller holes, so we don't get the same expansion ratio, but now we have the chance to put work into the foam to develop a structure. And you can see now the drainage time is almost 9 minutes. So that structure gives us a much better drainage time. And I think the key thing with PFAS-free foams is really developing that foam structure to give the foam properties that we need to counteract the loss of the PFAS. We don't understand everything, but I think we can infer the properties and also the fire performance of foams from looking at the physical chemistry of the formulation and understanding what those different components give to the foam formulation and how that affects the fire performance. And so these techniques, these classical surface techniques, can be used to inform effective foam formulations. So which components should be used, what ratios. We can use them to look at new materials or new mixtures, and we're pretty certain that to develop better PFAS-free foams, we will need to look at new substances that haven't been used before, and it will lead to improved foams with better properties and better performance. And I think the key to all of this is in polymers and really understanding polymer surfactant interactions, and that's where we're going to understand how to develop these foams. As we know, the DoD is looking for a biodegradable, PFAS-free drop-in replacement for AFFFs. And I think what this work shows us is that foams based on hydrocarbon surfactants can perform well. They can perform on heptane and gasoline fuels. We get a decent level of performance in both fresh and seawater. And this is at the existing application rate and the existing hardware that's used in the current test. So I think what this work tells me is that the ongoing efforts to develop PFAS-free replacements are worthwhile, that the logic behind them is sound, and that they should continue, and I would certainly support that. So thank you for listening. Do you have any questions?
Thank you so much, John. We did receive a lot of questions. Let's start with a first one from the Michigan Department of Environment, Great Lakes, and Energy. We know that you stated very clearly in your overview slide that your project is not evaluating siloxanes. Can you just elaborate a bit about the concern for using siloxanes as an alternative in foam?
Yeah, siloxanes are a man-made chemical that does not exist in nature. So we know with hydrocarbon surfactants, hydrocarbon materials have been around for millions of years, and so nature has had time to develop bacteria, enzymes, or other mechanisms for breaking them down once they get into the natural environment. Siloxanes, because they're man-made, have only been around for a very short number of years, and those biological degradation mechanisms don't exist. That there are no organisms out there that can degrade siloxanes. So for me, siloxanes is just a PFAS waiting to happen.
Great, thank you so much, John. This next question is has to do with infrastructure if and when we switch from AFFF to PFAS-free foam. Can we use existing infrastructure, or can existing infrastructure like mixing tanks and nozzles be used for these newer foams or modified for newer foams, or are we talking about a complete rehaul?
The goal would be to have a complete drop-in replacement. So it has the same physical properties as an AFFF, and it has the same, develops the same quality of foam. And that way, all we would need to do will be to replace the foam concentrate from PFAS to PFAS-free. We'd need to do a good cleanup procedure of any equipment that was contaminated, but we should be able to use existing pumps, tanks, nozzles, piping, proportioners, if the physical properties are the same. Now, the issue we have is that AFFFs are generally very low viscosity, and they're very easy to pump, and they have a certain range of equipment that's used with them. And historically, a lot of PFAS-free foams have been very viscous, non-Newtonian concentrates that require special equipment. And what we're trying to do is develop PFAS-free foams that don't contain those high molecular weight polymers, but which have low viscosity, Newtonian behavior. And as far as possible, we can use existing equipment. Maybe existing equipment with a little bit of adjustment, but certainly what we don't want to do is force everyone to replace their entire foam systems, because that will be very expensive. If we can just replace the foam concentrate, I think that's a much better option.
And two follow-on questions related to this. What about cleaning the existing infrastructure to remove PFAS is one question. And a follow-on question, when you're talking about dropping in a different formulation, what is the limit on how viscous a formulation might be that could still lead to a drop-in product?
Okay, well, the first question, clearly PFAS are quite difficult to clean up from systems because they have very low water solubility. And that's one of the weaknesses of PFAS, is they're not very soluble. So cleaning them up is difficult, and there is a lot of work being done on how to clean up existing systems. So I think it's probably best if I don't say too much about that, other than there is a lot of work going on, and ideally you would clean it until your water showed no detectable PFAS. And the second question, in the European standard, European 1560X standard, there is a viscosity limit of 120 millipascal seconds at a shear rate of 375 reciprocal seconds at the lowest use temperature of the foam concentrate. And that is the limit that they define for needing special equipment. So I would say that if your foam concentrate is below 120 millipascal seconds at that shear rate at its lowest use temperature, then you should be able to use existing equipment. And that's from the European standard.
Great, thank you so much, John. All right, this next question, based on your studies so far, will PFAS-free foams likely reach the same level of fire performance as fluorinated foams or AFFF?
Okay, that's quite a complicated answer, because I think in fresh water, the answer is yes. And if you look at PFAS are very good at extinguishing, but their burn back performance is quite poor. I think already we can see PFAS-free foams that have much better burn back times than PFAS foams. The challenge that we still have to face is the extinguishment time, but I think in fresh water, we will probably have a foam next year that will meet that 30-second and 6 minute time that's in the mil spec on the 28 square foot pound with gasoline. I think in seawater, it's harder, and that's going to take a bit longer. But I think the freshwater product should be available quite soon. I think we'll probably manage that next year. And apart from the mil spec, I think almost every other standard or test method we can already meet with PFAS-free foams. So, for example, UL, EN, IKOB, and C, we can do all of those now with PFAS-free foams. The MIL-F is the last one, the last remaining standard that we haven't yet managed to pass, but we're getting there.
Thank you, John. The firefighting foam industry is a relatively small one. Are there bigger industries with similar issues that we can learn from as far as technology and technology deployment and technology development?
One of the problems we have with firefighting foams is the industry is quite small in terms of volume of chemicals that we use. And so most of the surfactant manufacturers and polymer manufacturers won't make materials just for us. So we have to try and borrow materials from other industries. And that could be anything that just happens to have the right material. An industry I've looked at quite a lot is oil recovery, because it's about generating foams in quite harsh conditions, so seawater, maybe high temperatures, and using it to emulsify fuel. And though we don't want to emulsify fuel, we can get some quite good learning from the papers that are published there. And that's a much bigger industry, and there's a lot of work being done there, a lot of publications we can look at for ideas.
Thank you so much. Let's shift gears a little bit to talk about timelines for development and deployment. When does DoD need a new firefighting foam formulation by? And how far is this approach away from deployment? If you can elaborate on the timeline, you touched on it, but if you can elaborate, that would be appreciated by our audience members.
The difficulty we have is that the current MIL-F 24385F standard is for PFAS foams. In fact, it even says one of the clauses is the foam must contain fluorocarbons. So a PFAS-free foam can never pass that spec. And what we're waiting for is for a new specification to come out that says, here's what a PFAS-free foam has to do. Here's the fire performance, here are the physical properties, here's the corrosion, and all those other things that are in the specification. And I suspect it's a bit of a chicken and egg situation in that you can't write a spec until you know what products are capable of, and we can't develop a product until we have a spec. So it's a sort of a difficult situation. So what we're trying to do in the absence of an actual defined specification is we're just trying to get the best performance we can in both fresh and seawater, using the existing spec as a guide. So we're using the same hardware, same application rate, same fuel, same pan size, and trying to match the standard that exists at the moment. But obviously we are waiting for the new spec to come out so we can then see how close we are and what else we need to do. But I think in terms of a 28 square foot gasoline fire, I think, as I say, we're probably not too far off now. I would expect us to be able to meet that next year.
Thank you, John. I'd like to go ahead and pull Ezra back in the discussion because we have some outstanding questions for him. And we'll wrap up, John, with another question for you. And then we'll stop at exactly 1:30 p.m. Eastern. So Ezra, two questions for you related to the catalyst that you use. How stable is the BOHP catalyst, and does it need to be replaced after a period of time?
Right, that's a good question that I think is not well understood for BOHP nor for really any photocatalyst. We often see people publish experiments showing that they reused the materials around 5 times and observed nominal decrease in activity, but of course, for actual application, you'd probably want the catalyst to last for weeks of continuous use. We found that BOHP is certainly less stable than we would want it to be, but it's inconsistent and kind of depends on the conditions of the reactor. If the water becomes oxygen depleted, the catalyst loses stability. At least that's what we think so far. And it changes color. It goes from being white to sort of an off-white or even a gray. And that's indicative of electrons being trapped in oxygen vacancies and forming charge recombination centers. So potentially the catalyst could be taken out after some time and maybe chemically regenerated, or perhaps done in situ with an oxidant that would strip those electrons out of the surface vacancy sites. We're not quite sure about that, but we are very interested in this question, and also the extent to which we can control oxygen vacancies in the bulk particle semiconductor particles, which might lead to some improvement in this ability.
Thank you, Ezra. And another question related to the whole catalyst issue. When you move to a full-scale system, how are you planning to capture the catalyst particles and potentially reuse them? Is that a possibility or a likelihood?
Yeah, it'd be similar to the way the commercial units that I showed works, which uses a ceramic ultrafiltration cross-flow membrane system. So the catalyst is contained within a slurry loop on the feed side of that membrane and gets continuously cycled through while the effluent water penetrates through the membrane and then can escape. So it could be operated in a flow-through configuration where raw water comes in, clean water goes out, and the catalyst is retained and recycled.
Thank you so much, Ezra. And then a final question to John before we wrap up. You answered a lot of the bigger picture questions, John. This is a bit more nuanced. Can you comment on ways to improve the bubble expansion ratio using compressed air or other methods?
Yes, the way that, that most nozzles work is they pump the foam solution at high pressure past some air holes, and so the Venturi effect drags air into the foam stream where it's then stabilized by the surfactants. There are compressed air systems that actually inject air, or could be another gas, could be nitrogen, into the foam stream, and that's a different way of generating foam. And generally, that gives a very good quality foam. You can get good expansion ratios, very nice bubble size and bubble structures. So that produces very good quality foam, but it's not a drop-in replacement. It would require a lot of new hardware if you wanted to use that sort of foam more widely. So really, I think that the goal remains, can we develop a high-performing foam using existing hardware rather than those compressed air systems?
Thank you so much, John. And thank you also, Ezra. You've both done a great job with your presentations and the Q&A sessions. It is now time to wrap up. I'd like to remind you that our next webinar, which is part 2 in this series, the AFFF series, is in 2 weeks on Thursday, September 23rd. This webinar will feature 2 speakers, one from the Environmental Restoration Program area and one from Weapons Systems and Platforms. We will feature Joe Quinnen at Arcadis together with Terry Reed from Aqua Aerobic Systems, and they'll talk about a sustainable groundwater treatment technology for PFAS removal. And our second presentation will focus on modular design strategies for novel formulations of PFAS-free firefighting foams, and that will be presented by Dr. Tim Long at Virginia Tech. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I'd like to echo Robin's reminder and let you know that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would really appreciate it if you can please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your participation.